Our next speaker, Trenton Cladouhos, will be talking about something very, very hot. We're talking about geothermal here.
Okay, I'm going to be talking about an energy source that hasn't really even been mentioned yet. It was a tiny little wedge on Tyson's graph, and you haven't heard anything more about it. And that's geothermal. This, of course, is very quick. I encourage you to go to our website for the full presentation that we've done. Okay, so I'm going to be talking about the same thing everyone else is. How do we meet the future electrical demand with clean power? We know that solar and wind are growing and are a big deal right now. But of course, we've all heard about the challenges of keeping that grid running with these intermittents. So we went back to the drawing board and thought, well, what is the ideal energy source? It's dependable, flexible, widely deployable, high energy density, free fuel, and low cost. So I'm going to be talking about enhanced geothermal systems. How do you create an EGS? You drill an injection well, pump cold water into that well to create permeability at depth. Once you've created that permeability, you drill production wells into there and then circulate water through the heat exchanger you've built in the hot rock to spin a turbine and generate electricity. So right now, the US geothermal resources are all in the West. There's about 3.5 gigawatts in the Western states. If we do traditional EGS, we can do about 2.3 terawatts in the continental US. But the problem is it's not quite economic right now. And the key is if we look at the energy per well, because the wells are an expensive part of the EGS. So if we drill a gas well and burn that gas, we can get about 10 megawatts of electricity for a 3-kilometer deep well. Conventional geothermal, 2-kilometer deep well, 7 megawatts. The current EGS at cooler temperatures, 200 degrees C, is about 5 megawatts. If we go super hot, drill 5 kilometers, produce 450 degrees C fluids, we can get 40 to 50 megawatts per well. So 10 times more efficient than the current EGS and 5 times better than the natural gas well. And that's because temperature really matters. If we want to drill or create a 100 megawatt utility scale plant, we're going to have to drill 42 wells to get to that. 24 producers, 18 injectors. If we get 400 degrees C fluids, we only need 2 producers and 1 injector. And the footprint is going to be far smaller as well. 1 kilometer versus 30 kilometers at the surface. So EGS can meet the market if we go hotter and deeper. And we're basically directly tapping the heat source. At temperatures over 400 degrees C, we get 10 times as much production per well. And after we go hot, we can go deep. We can go deeper down to 10 kilometers. And that allows us to expand this idea of Superhot EGS globally and go anywhere. We've done the comparison of levelized cost of electricity. We think we can produce Superhot EGS for $46 a megawatt hour or 46 cents a kilowatt hour. That really beats all the other renewables, especially when you start adding in storage for solar PV. And it also beats EGS today which is about $80 a megawatt hour. Where can we do this? Pretty much we can do it anywhere you see red on here easily. Iceland has got a head start like everything in geothermal. They've drilled a super hot well. We had a workshop in Bend, Oregon just a month ago to talk about it in our Newberry site. So let's look at reliability. That's already come up quite a bit. Problem is wind and solar are off 70% of the time. They're not producing. Super hot, the earth is always hot. It's base load. It's always available. So you don't have these issues of reliability. What about energy density? Of course, wind and solar have to cover a lot of land. In contrast, geothermal is a very small footprint because all the energy is under our feet. So you don't even see where all that energy is being produced. You just have a small power plant at the surface. How do we get global penetration of this idea? We need to assemble the dream team for geothermal, start innovating the required breakthroughs because there are some, and start demonstrating this at sites, iterate, and then go deeper and hotter as needed. So we can start in magmatic areas. We have a site in Newberry volcano in Oregon. The first thing we need to do is figure out how to drill to 400 degrees C, and, create wells that'll withstand those heats, and then how we create the reservoir in these super hot rocks, because it's going to be different the higher temperatures. The rocks are more ductile. Once we figured it out at shallower temperatures, say 5 kilometers, we need to start going deeper, 10 to 20 kilometers, and we're going to need some next generation drilling equipment. Energy drilling, for example, is one way to do this. Once we, in the 10-year plan that we have, our idea is to go to Newberry volcano in Oregon, generate about 6 gigawatts. That's enough to power all of Oregon. Then we can go to the western U.S. states, 8 states, and power a significant portion of the West. This will balance that intermittent renewable generation we talked about. So Superhot EGS is the ideal energy source. It solves a lot of these problems. It's dependable, flexible, widely deployable as long as we can go deeper, very high energy density, low environmental impact at the surface. The fuel is free, and it's low